Assalamualaikum. My name is Tahir Naseem, and today I'll present my work on emotion recognition through multimodal Ph.D. and deep learning models. In this talk, I'll focus on how combining visible, infrared, and multispectral imaging together with advanced deep learning architectures can improve the robustness and accuracy of emotion recognition systems. I'll also briefly describe the datasets, some of the well-known datasets, and then I'll tell about the datasets which have used in our one of our proposed methodology and some key performance outcomes, followed by the applications and future directions. In this presentation, I'll first introduce the concept of emotion recognition and its importance. Then I'll outline the main problem statement, emphasizing the technical challenges in current systems. Next, I'll explain the multimodal Ph.D. approach, followed by an overview of deep learning models used for emotion recognition. After that, I'll discuss the datasets and methodology, including both single model and multimodal datasets. I'll then present our proposed methodology and the performance measures used for evaluation. Finally, I'll highlight some key applications, discuss some future directions in this field, and then I'll conclude this talk. So, emotion recognition aims to understand human emotional states by analyzing facial expressions, body language, and various physiological signals. It has become increasingly important for human-computer interaction where systems must respond appropriately to user emotions. In healthcare, emotion recognition can assist in detecting stress, anxiety, or depression, and in security applications, it can support behavioral analysis and threat detection. In this work, my focus will be on multimodal Ph.D. where we can combine multiple modalities like visible, infrared, and multispectral data. This multimodal strategy or mechanism is designed to enhance the robustness and accuracy of emotion detection, especially under challenging conditions. So, this is problem statement. Despite significant progress, emotion recognition still faces several challenges. One major challenge is occlusion, where facial regions are partially covered by the objects such as masks, glasses, or hands, which can hide critical expression cues. Another issue arises from environmental factors, particularly illumination changes, which strongly affect the performance of methods relying only on visible spectrum. Additionally, there is substantial variability in how different individuals express the same emotion, leading to inconsistencies and intra-class variation in the data. Together, these challenges limit the reliability and generalizability of traditional single model emotion recognition systems, and they motivate the need for more robust multimodal approaches. So, here comes multimodal Ph.D. approach. To address these limitations, we adopt a multimodal Ph.D. approach that integrates information from multiple modalities, visible, infrared, and multispectral imaging. The visible RGB modality captures rich texture and appearance information from facial expressions but is highly sensitive to lighting conditions. Infrared imaging, on the other hand, detects thermal radiation and captures subtle changes associated with the muscle activity and blood flow, maintaining performance even in low light environments. Multispectral imaging extends this further by capturing data across multiple spectral bands, providing deeper insights into skin and tissue properties. By fusing these complementary modalities, we aim to build models that are more robust to occlusion, illumination changes, and inter-subject variability, thereby improving overall emotion recognition performance. So, deep learning plays a central role in recognizing every problem. In our role, deep learning also played a very vital role. Convolution neural networks or CNNs are used as a primary feature extractors, learning discriminative spatial features directly from the image data. For scenarios with temporal information is important, such as video sequences. Recurrent neural networks can be used to capture the evaluation of facial expressions over time. We can employ Phi networks, which are multi-stream architectures designed to integrate features from visible, infrared, and multispectral inputs either at feature level or decision level. To improve the training efficiency and performance, we leverage pre-trained models using transfer learning, adapting network trained on large data sets to our emotion recognition tasks. This combination of CNNs, temporal models, and Fusion architectures forms the backbone of our deep learning based multimodal systems. In this section, I'll provide an overview of datasets and methodological pipeline. We classify datasets into two broad categories. One is single model and other is multimodal. Single model datasets contain data from only one modality, such as visible, visible or RGB, or infrared or multispectral or physiological signals. In contrast, multimodal datasets combine information from multiple sources, for example, visual, infrared, and multispectral, and sometimes even audio or text could also be included. Our methodology, which I'll explain later, involves carefully selecting representative datasets from each category, applying some pre-processing steps, and then deep learning models tailored to single model and multimodal setting. For this single model evaluation, we rely on well-known facial expression datasets. So, basically, I want to say that this slide shows you some of the well-known single model datasets. Like 𝗠𝘂𝗋+1 is a classic laboratory control dataset consisting of posed facial expressions with clear labels, making ideal for benchmarking. And then 𝗙𝗵𝗿 dataset focuses on Japanese female facial expressions and is widely used in early emotion recognition studies. And 𝗘𝗺𝗫𝗂𝗃 includes both near infrared and visible light images, allowing us to explore performance under different illumination conditions. 𝗏 2013 is a large dataset of about 35,000 grayscale images collected in the wild, real time, capturing more realistic variations. Then there is a 𝗟𝗲𝗿 dataset. It's a real world affective faces database, which contains in the world again a real database having facial expressions with diverse poses and backgrounds. Then AffectNet provides over 1 million facial expression images. It's a large dataset labeled with various emotions, offering a rich resource for training deep learning models at scale. Then comes multimodal datasets like MAFW dataset or a multimodal affective database in the world, which includes both video and audio clips, enabling joint analysis of facial and vocal cues. HEU emotion provides video data along with the body posture and speech, which is useful for studying whole body affective behavior. Then the VIRI dataset, which is important, and it includes visible, infrared, and multispectral images. And then NVI dataset also contains visible, infrared. It doesn't contain multispectral images. Then there is MELD, which contains a multimodal conversation data with video, audio, and text. Then there is emotic dataset, which focuses on emotion recognition in context, capturing both the subject and surrounding environment. These multimodal datasets allow us to evaluate the benefits of Fusion in more realistic and complex scenarios. So, basically this slide shows our datasets which I have used in our proposed methodology. Basically, here I want to present some of my work which I recently published. So, this slide basically few samples from our two datasets. Figure 1 shows few of our samples from a well-known dataset VIRI. It's a multimodal datasets. In the first column, as denoted by all the images are captured by the visible or RGB sensor, while the images in B shows all the images captured from the infrared sensor. Similarly, the column C shows all the images captured from the multispectral imaging. So, basically there are 3 sensors and capturing capturing the same expression of same subject in three different scenarios. Similarly, there is another data set as shown in figure 2, it's NVI database. The A part shows the visible images, while B part shows the infrared images, and from left to right the images are shown expression wise. So then here comes pre-processing. Pre-processing is very important step when we need to train our machine learning or a deep learning model on a specific kind of a data set. So the challenge was basically there were insufficient of images we had in our data set. For example, in 𝗿𝗏 we had only 550 images, and we know very well to train a deep learning model we need a large data set. So definitely we need some augmentations. So in our work we did augmentations offline. Offline mean we applied some augmentations and increase the size of the data set on the disk. So what kind of augmentations we applied? So basically in the table 1, if you see in our data set there were 5 classes: angry, happy, neutral, sad, surprise. So we divided the image into 3 parts. We divided the data set into 3 parts: training, validation and test. So training mean the training set will be used to train our deep learning model, while the validation set is used to tune the hyperparameters of a deep learning model. While we separated the test part, so it couldn't be used in the training part. So once the model is trained, so we will use the test set to just get predictions from our best trained model. So the augmentations we use: rotations, zooming, distortions, shearing, flipping, and we applied 5 times rotation, 5 times zooming, and so on and so forth. For example, as you see in the second column, so these are total number of images expression wise before augmentations. So when we applied augmentations, as you see, we applied rotation 5 times, zooming 5 times. So before augmentations the total number of angry images were 77. After applying augmentations, the images in angry expression were 2002. Similarly, for angry expression the validation images were 16 and test set were 18, and similarly for other expressions. So in this way we increase the number of images by using augmentation, so we can train our deep learning model to get better accuracy and to make a model more robust. Basically there are so many ways to get augmentations, like we can use the generative AI, GANs, LLMs. There are so many ways, but to make our model more simple and to make it applicable for the real time, we just use offline and simple augmentations to increase the size of this data set. Since in our proposed methodology we use 2 data sets, so this methodology I have told you is just used for 1 data set. Similarly, we can use this strategy for other data sets we have used in our proposed methodology. So then here is performance measures. To evaluate our models, we compare the performance of traditional single model approaches, which uses just one modality, visible, thermal or multispectral. The main performance matrices include accuracy, precision, recall and F1 score, which collectively capture classification correctness and class-wise balance. We also analyze how early Phi-n and late Phi-n strategies affect results. I will explain these terms later, what is early Phi-n and what is late Phi-n. Looking at whether these combining features at immediate layer or combining final decisions gave better robustness. So basically these are our proposed models for single models. Basically our main thrust or purpose to develop multi-model systems. So, but how we can compare that our accuracy or some other performance measure of multi-model is better than some system? So definitely we need some baseline. So figure 3, figure 4, figure 5, So these acted as a baseline. So here comes our multimodal approach. So basically in the bracket there is written 𝗟𝗲𝗰𝗏. So 𝗟𝗲𝗰𝗏 basically mean we are concatenating the features. Basically we are getting a three modalities: visible, infrared and MSX, and again we are passing all of these modalities to the ResNet with last layer modified as we discussed before in the single models. This was the modified layer of ResNet for visible, this is for infrared and this is for MSX. So here we got the features for all these modalities, and we concatenated the features in row wise. So basically first I got the feature vectors for visible, then from the infrared and then from the MSX, and then I put some activation function ReLU, and again as I told you about the softmax, and then we trained the classifier and classify the 5 expressions which were available in our data set. But the thing is here we use two kinds of training. So one is called a one-step training and one is called a three-step training. So one-step training means end-to-end training. So the model is trained from end to end. The other is one-step training is also called a end-step training, end-to-end training. Similarly, in three-step training, we train the model further from one-step training. So in three-step training, what we did, we trained the model first in one-step training and we saved the best model. In three-step training, we loaded the same model which we trained and saved for one step, and it again we fine-tuned it in three-step training. So by using this kind of mechanism, a kind of three-step training, we improve the performance by using three-step training as compared to the one-step training. Similarly, this is again our second multimodal approach which uses 𝗏𝗏𝗰𝗏. 𝗏𝗏𝗰𝗏 mean we ensembled the outputs of same models which in easy terms we call as 𝗏𝗏𝗰𝗏. So in ensembling, whether we can use the same model or whether we can use a different model. So in cumulative sense, so the modalities could be different. So first we use visible and infrared, then we use visible with MSX, and in the last we use visible, infrared and MSX, all three modalities together. And similar kind of mechanism was used in 𝗟𝗏𝗰𝗏, mean first we fuse the features from visible and infrared, then we fuse the features from visible and MSX, and in the last we fuse the features from all three modalities, visible, MSX and infrared. So these are some our results in the form of a confused matrix. So this confused matrix is for visible, this is for infrared, while this is for MSX. So for visible, overall around 82% accuracy was achieved. For the angry class, around 72.22% images were expressed as angry, while no single image was classified as happy. It means there is very less misclassification for happy expression. Similarly for other. In case of infrared, which is figure 9, the overall accuracy was 50%, which was less than the baseline, and this was our drawback of our proposed scheme, and we know every research has a drawback, but we improved it later by using attention mechanism, and due to the time constraint I couldn't propose that methodology here, but we improved it later on. Similarly, this confused matrices is for our MSX data set, and one thing which is very important, these three confused matrices are not for training, not for validation, it's for test set. mean we trained the model, we validated the model, so then we tested the model and got predictions which the model didn't saw when we trained the model. Similarly, these confirm matrices for one-step training and these confirm matrices for three-step training for one-step training and three-step training for early Phi_n. And this column is for one-step training and this column is for three-step training for our first approach, which was multimodal feature Phi_n. And it's very obvious, it's very clear from the confirmed matrices from second column, from the first column, that the accuracy of second confirmed matrices in the second column are better than the accuracy of confirmed matrices in the first column. So in this way our three-step training worked and it performed better than the one-step training. Similarly, then this slide shows some applications of multimodal emotion recognition. So multimodal emotion recognition has a broad range of applications. In healthcare, such systems can help monitor stress, anxiety or depressive symptoms in patients, enabling early intervention and personalized treatment. In human computer interaction, emotion-aware interfaces can adapt content, feedback or difficulty based on user emotional state, creating more natural and engaging interactions. In security and surveillance, emotion recognition can support the detection of distress, aggression or deceptive behavior, complementing traditional biometric systems. In the automotive domain, I'm working in the domain of automotive vehicles by proposing facial expression systems for the autonomous vehicles. So in the automotive domain, emotion-aware driver assistance systems can monitor driver fatigue, frustration or distraction and adjust alerts or control strategies accordingly. Then there are some future directions. Looking ahead, there are several promising directions for advancing multimodal emotion recognition. First, hardware advances are making multispectral and infrared sensors smaller, more affordable and more energy efficient, which will facilitate their integration into consumer devices. Second, improved Phi_n techniques such as attention mechanism and self-supervised learning, we did this one, can better exploit cross-model relationships and reduce the need for large labeled datasets. Cross datasets mean we train the model on one dataset and test on other dataset. Third, there is a strong need to explore cross-domain applications where models trained in one context are adaptive to different populations, environments or sensor setups. Addressing these challenges will move multimodal emotion recognition closer to reliable large-scale deployment in real-world systems.